All right, so most of the time, most people actually, when we want to approach a problem, we want to solve a problem, we use our understanding, our knowledge, our intuition about the problem, and also about our past experiences. But that's not a scientific and systematic way to address that. So what we want to do in actually this lecture, in actually this course, is to learn the scientific and systematic approach to that. The decision science, or also the management science, it's about that. It's about using a systematic and scientific way and approach to problem solving or decision making. And it is based on logic, and it is data driven, and it has a systematic approach. And most of the time, and especially in this course, we're going to use the mathematical model. So that means that we're gonna use models that use symbols and equations and numbers and etc. And we're gonna use the data that we get from the problem, a real problem, and then we're gonna work with that with the model to get the solution for that problem. So during the past 60 years, in these sciences that I mentioned, the decision science or operation research or management science, there are different names. They actually overlap a lot. There have been a lot of actually findings and new models that have been built for different actually type of problems. So there are a lot of different actually quantitative models that we can use for different types of problems. You might have heard about business analytics. So what is the difference between business analytics and decision science? Actually, they are a lot similar to each other, except that in business analytics, we're not actually optimizing as we do in operation research, for example, in linear programming or integer programming, mixed integer programming, nonlinear programming. We are analyzing and making sense of the data, or and making a prediction, etc. But one of the main differences is actually the size of the data. So in business analytics or in data analytics, we work with large data. Okay? So in this course, we're gonna use different types of quantitative modeling, specifically in spreadsheet, in Excel, to solve a problem. All right, what is a mathematical model? So a mathematical model is just a bunch of numbers and equations and symbols that we use for different to represent the relationship between different aspects of a problem. For example, variables, we have parameters that they don't change, and we have the decision variable that's up to us. We can actually control it, and then there are, for example, an objective that we want to optimize, we want to control. So we're going to use this mathematical model to represent the problem, these different aspects of the problem, and also the relationship that there is there. So a quantitative or algebraic representation of a real problem. A typical model features numerical data. So numerical data, or inputs that we have, or parameters, those are the data that we get from the real world problem, from any system that we want to study. So these numeric data doesn't change. We also call it parameters. And so we have another feature is decision variable. So decision variable, first of all, it varies. That's why we call it variable. So that means that the number or the output can change based on this. And it's based on our decision. So it's in our control. And there are assumptions made into every mathematical model, every other model, because we can't really have the real problem formulated into a bunch of symbols and numbers, right? So we have to make simplification assumption to make the problem easier to model. Otherwise, we won't be able to actually model a realistic problem. But there are different aspects, a lot of different dynamics that we might not actually understand. So that's what there is actually a popular saying that all models are wrong, but some are useful. This is a very famous um, saying about the models in management science. And when you actually build a model, you can always try to improve it and try to get rid of some of the major assumptions to make it more realistic. But ultimately, it's not really possible to have all the assumptions taken away. And also, other parts of a model is the equations or inequality that shows the dynamics of different relationship into the problem. And after we have this model, there has to be a scientific mathematical approach to solve it. Luckily, we actually have a lot of different softwares that can actually solve this problem. So, for example, even in Excel has a lot of it has that capability, and also for optimization, it has a solver which can use to solve these models that we're gonna build in Excel. An example of that is the break-even model. So break-even model, if you remember from accounting or finance or operation management, if you have taken if you're business major. So in break-even model, we have like a cost and we have revenues. So we want to see that the cost has two parts. You have fixed costs, that no matter how many items or things you produce, you're gonna have to pay for that cost. For example, renting of a space for a manufacturing site, or building that, or for the machineries, equipment. No matter you use it or you don't use it, you produce, you're gonna have to have that fixed cost. And also we have variable cost that's going to depend directly on how many you produce. That's going to be. And on the revenue side, we're going to have the demand, or how much you actually have produced and you can sell. So that's the quantity multiplied by the price by which you can actually sell. Right? So we want to see what is the break-even point. That means that at one quantity that you produce, your total revenue is equal to your total cost. That means that you haven't lost any money, you haven't gained any money either, right? So that's the break-even model. So that's a simple, actually, problem that seems to be able to just with few equations and numbers you can actually solve, right? All right. So descriptive and prescriptive. Descriptive models are based mainly statistics. It's about the relationship between data. Prescriptive models are, on the other hand, optimization. When you want to, for example, minimize or maximize an objective function. For example, you want to minimize the cost of production, or you want to maximize your revenue. Right? So those are called prescriptive models. All right, so let's just start with a simple model. This model is called the tipping point model. It's actually related to the current situation that we have, which is COVID-19 or coronavirus. So suppose that 100 Canadian tourists arrive in San Francisco today, and they're carrying an untreatable 24-hour flu virus. I don't think we have Canadian here, but no offense, this is just an example problem. All right, so we have 100 Canadian, they carry a virus 24 hours, last 24 hours. Okay. And we have this flu virus has an infection rate of 2%. Okay. That means that if one person that is infected is in contact with a healthy person, there is a 2% chance that that person get infected in that contact. Or if you are, out of 100 people, there will be an average 2 people infected if they are in contact with this person. Also, suppose that the contact rate is 50 people per day. That means that on average, we assume that each of these Canadians that are infected and they are in contact with 50 people on average. And so that's called the contact rate. Okay? So these are inputs that are very important actually to the outcome of the problem, as we're going to see later when we model this problem in Excel. But you might actually also figure out of your intuition that these numbers are important. The infection rate and the contact rate. These are also can be or are used in coronavirus modeling. Although coronavirus modeling is going to be much more complicated than this model that we're going to solve here, but we have to start with a simple model because this is our first model. So this is the problem. What conditions tip the situation into a pandemic? So if you have this problem, the 100 infected people with a flu virus that lasts 24 hours, and by the way, that means that if a person is infected today, we assume that tomorrow after 24 hours doesn't have the virus, magically disappear. But we can also change this incubation rate or the spread as well. And 2% infection rate, the contact rate is 50. So what conditions would tip this situation into a pandemic? How many people will be infected after 10 days, 20 days, 30 days, etc., etc. These are the kind of questions that we want to answer. Without having a model, just looking at this problem, as I mentioned it here, I think you can agree that it's not that easy to answer this question, right? But just knowing that there are 100 infected people with a virus that would last 24 hours and the infected rate of 2% and a contact rate of 50, I don't think that any of you could tell the class that what is the tipping point here that would actually turn this virus into a pandemic, right? Or what would be the number of infected after 10 days, right? So we need to do some computation, okay? So we need to do some calculation analysis here. So this is what we want to do. We want to do actually a model here. All right, so let me stop sharing this and go to Excel file. So try to not just be a passive observer. I think it's going to really help you if you actually do the modeling with me. So try to open up an Excel file and start modeling with me. Let me open up an Excel file here. Okay. All right, so this is an Excel worksheet which is empty. And we're going to put the information that we have here. So the tipping point model or tipping point problem. First, I'm going to put the inputs here. The inputs we have, what do we have here? We have the initial infected people, the number of people. And we have, and that was about 100, right? So at the beginning, there were 100 people infected. Okay. Okay, so let me make some changes here to make this more readable. Then we have the infection rate, which was 2%. Okay. All right. So as you see here, any numbers that I put here, I have this option here that I can specify what type of number it is. If it's a general number, just number, it's a currency, it's date, time, etc., etc. So for this one, it's percentage. And if you remember, I just put 0.02 and it turns into 2%. Okay, so that's infection rate. And the other one was the contact rate. The contact rate was 50. And we also had the population size. So the population that we're talking about, San Francisco, we assume that the population is about 850,000. Yeah. So these are people, number of people. This is contact rate is so people per day. This is also number of people. All right, so that's our inputs. That's the information that we have. Next, we're gonna have, so to answer the question, one of the question was, well, what happens after 10 days? What happens after 20 days, 30 days, etc. And so that's one question, the number of newly infected. So we need to compute actually the number of newly infected, okay? So suppose that we are talking about, we want to talk about the number of days. For example, day one. For day one, here we start with the number of people with flu at the beginning. Number with flu. Okay. So day one, we have actually 100 people with the flu. Okay. And that's actually given input. Okay. So instead of like putting in 100 number here, it is best if we actually build a model that is dynamic and it's automatic. Okay, so you don't have to go to the calculation to change things. Okay, it's better to, if you specify that your model actually would work with different inputs. Okay, so so that if I change the input from, for example, instead of 100 people infected the first day, if I change it to 150 or 200 or 50, whatever, I wouldn't have to go and change this number everywhere else. So that's why I'm going to use actually I'm going to actually link this number here. Okay, so that if I change this later on, it would actually stay the same. So that's the first column is the number of people with the flu, and then is number contacted. So the number contacted, if we have 100 people at the beginning that are infected, and the contact rate is 50, that means that each infected person on average would contact 50 people. That's 100 multiplied by 50, okay? But I'm not gonna write 5,000 here. I'm gonna actually link this to make it automatic and dynamic. So that would be 50 multiplied by 100, which is 5,000, right? And in the next information that we want to have here, let's go up here. That's the number of people newly infected. Okay, so the number of newly so how we can actually compute this number, the number of newly infected. So the number of newly infected is related to the number contacted multiplied by that's the total people that have been in contact with the infected people. which is 5,000. And out of these 5,000, actually, not every one of them is going to get infected because of the infection rate. So out of these two, only 2% of them are going to be infected. Okay, so the number of infected here, therefore, it would be this 5,000 multiplied by this 2% here, okay, which is 100. All right, so we have it for the first day. At the first day, the initial number of infected people were 100. The number of contacted people, 5,000, 100 multiplied by 50. And the number of newly infected are 100. Okay. All right, so let's see what's going to happen at day 2. So suppose we're going to do this for day 30, until day 30. Okay. So a nice thing about Excel is actually you can actually copy or drag some of your computation and cell into other cells so that the computation is automatically going to paste into other cells. So the same computation is going to go into other cells as well, as we're going to see here. But there is a caveat here. If you remember, I put the B5 here. Okay, so if I for day 2 here, so for day 2, the number of infected for day 2 is actually the number of newly infected. So I have to make it equal to cell D and 12 here, okay? Because the flu is 24 hours. After 24 hours, it's not going to last. So if there are 100 people today and they contacted with 5,000, tomorrow they're going to be 100 people, but a total of 100 people, because the people who are today, they had the flu, tomorrow they don't have the flu. That's one of the information that we have. It's 24 hours, 24-hour flu. Okay, so that's why I put the day 2. I put the number with flu equal to the number of newly infected from day 1. Okay, but everything else is just going to be copied here. So I can actually copy this here by dragging it down. So it can actually come down to here. But as you see, the number actually exponential. It's actually too big. So what happens is, if you drag this down, so for example, that means that I copied this to the new cell. So what happens is, a cell that were used in computation also, they came one row down. So from 50 contact rate, it actually came to the population size, which is 850,000. Okay. So what we want to do is we want actually this number 50 to stay the same. So we call it absolute actual value of the cell. So to do that, this is what I'm going to do. I'm going to do input actually a $sign before B and 6. So now the position is going to be fixed. If I come down from here, I have to do it here. So I'm going to put the $sign here and here. Now, if I do that, it won't come. Okay. So the number of contacted would be the number with flu, which is 100 here, right? If you click in this line, it's going to show you with the color of a specified cell that we have. So B13 is shown with this red, red actually color here, and the blue one, which is for B6, which is the contact. Okay. So the number of newly infected, that's we can actually find out from the numbers. That's the number of contact multiplied by 2%. So again, this is going to be number of contacted here, multiply by, which is I'm using asterisk or star sign, multiply by this 2%. Okay. But again, because I want this to stay the same and don't move, I'm gonna have to put $sign before B and 5. So it's gonna stay the same. So now actually I can go up to 830. And now I can copy this. All right. So you see that these numbers actually are the same, stay the same for each day. The reason for that is because of this information that we have. It's because of the contact rate and the infection rate. Okay, so and these two inputs are very important. This is specific because the multiplication of the infection rate, which is 2%, and the contact rate, which is 50, is equal to 1. That's why each day we're going to have the same as we had before. That it doesn't change, right? So if we actually change this, the numbers are going to change. For example, if I change this to 2.1%, as you see here, the number is going to change, right? Or if I change it to 1.9% or any other numbers, the numbers are going to change. All right, so let me go back to 2%.
Professor?
Yes.
How did you fill it in?
Oh, you just drag it. You drag these cells. You actually click on this little handle that it is here and drag it down, which is equal to just copying and pasting. So instead of copying and pasting 30 times, I just drag it down.
Okay, thank you.
All right. So this doesn't look like, you know, as you see here, we talk about communicating the result, right? So you see here, we are just seeing a bunch of numbers, like 30 multiplied by 4, it's like 120 numbers, right? So one way actually to do that, as we say, picture is worth more than 1,000 words. Here we want to actually to graph this for better communication and better actually understanding of problems. So this is what I'm gonna do. I'm gonna actually graph this. So I'm gonna select all of these newly infected, and then I'm gonna come to the insert. Stays in my way. So you come to the insert, and there's a chart group here. Does everyone see it? There are different charts, and we're gonna use the scatter chart here. So I'm gonna use the scatter chart. There are also different scatter charts. I'm gonna use this one that has line. So scatter with smooth lines and markings. So I'm gonna use this one. Okay. So it's gonna produce this little graph for us. Okay. It doesn't have a name. It doesn't have any legend or anything else. Okay. So this is what I'm gonna do. First of all, I'm gonna call it. I'll give it the name. For example, I'm gonna go to tipping point model, and then I'm gonna put a legend on, or if you're on a Windows on a PC, if you click on this little plus sign here, it's gonna open up a window here. If you click or check on the axis title, it's gonna give you a title here that you can actually modify. Okay, so here on the x-axis, these are actually the number of days that we have. We have 30 days. Okay, so I'm gonna change this to days, and for the y-axis, that's the number of people that are newly infected. Okay, so I'm gonna change it to the number of newly infected All right. So now let's see if we actually, as you saw here, if we change these numbers, for example, 2% to 3%, and the numbers that's going to change, that also going to be influencing the graph for us. Right? All right, so let's see what happens. We have actually the number of newly infected people is, what is it, 20 million or something like that? 20 million, right? Which doesn't make sense because San Francisco has 850,000. Okay, so that means that we have to actually kind of modify our model here, right? It doesn't make sense to 20 million people. After 30 days, 20 million people in San Francisco are going to be infected. So there is something wrong here. And that's what we have here, okay? The number of contacted here that we have in column 2 here, these cannot exceed the population size of San Francisco, okay? So here, I'm gonna have to say equal to the mean and I'm gonna say B7, which is population of San Francisco. And because I want this to stay the same and doesn't move to other columns, I'm gonna put the absolute value sign, which is $sign before B and $sign before 7. Right. So now, if I drag this down, it's gonna be modified. So as you see here, after day 14, the whole population of San Francisco are infected, and it's not going to go up because it doesn't make sense. There are no more than people than 850,000, right? So it's going to stay the same as 255,000 as the number of newly infected people. So this is the number of newly infected people that's on the chart. The number of contacted is not on the chart. Right? You could also put this, the number of contacted on. All right, so let's now do a little bit of analysis here. For example, to see what would change if we have, instead of 100 people, we have 50 people. As you see here, it's gonna reflect that. Or if we stay at 2%, we stay the same. I'm going to go back to 100, and I'm going to change the contact rate to 51. So even as you see here, the contact rate from 50, if you just move one more person, the graph is going to be, it grows one. That means that the number of infected people would actually, that means the virus is going to spread. Okay? Or if I go to the 49 people instead of 50, it's going to go down. So that means that decaying the number of infected people from 100 is just going to go down to 60 or 54 after 30 days. Okay. So again, as you see here, by changing these inputs, our model is going to show different outputs. Okay. So this is a simple model which actually works. Any question here? Did everyone get the model going? Work? All right. So let's get back to our spreadsheet, our lecture slide. All right, so notes on tipping point model. We start with a simple model, as you saw here, and we actually, I actually modified it because it was wrong. If you remember, the population size of San Francisco were not reflected in the maximum number or the cap size of the number of contacted people, right? So you will start with a simple model and work on it, improve it, and also reconsider the after your model is done and you want to actually make another step, improve it, you can actually try to see the assumptions that are built into this model and try to relax that or make it more realistic. For example, here we talked about the duration of the flu to be 24 hours, which doesn't make sense. Like if you had flu today, you're going to have flu tomorrow, right? Or for coronavirus, the number of days that you are dealing with the virus is going to be, many days, right? So that's one of the assumptions that you can actually change. Or any other assumption that you see about your model, you can actually build on it and improve the model, make it more realistic. So try to refine the model. Perhaps obtain better input data. So that's also, you remember the popular saying garbage in, garbage out. So if you have garbage, that means wrong data or input, your output is going to be wrong as well, right? Experiment with the model parameters here. So we kind of did that experiment here. The infection rate is important. The contact rate is important. The population size is important. The initial infected people is important, as you see here. And this is kind of going to help you better understand the problem by figuring out or observing the relationship between these inputs and the outputs, right? So as you saw here in the terms that we had, for example, 3% is going to drastically actually increase, or if you have instead of 2%, they have 1.9%. It's going to decrease, right? So a little bit of change here is going to make a huge impact. Right. So did we learn anything about this after using this model? Yes, we actually learned a lot, and that's about these two parameters: the infection rate and the contact. Okay, so these are very important. So the infection rate, if we increase it from 2% to 1.1%, just one or tenths of a percent, it's going to have a huge impact. Or if we decrease it from 2% to 1.9%, it's going to have a huge impact. Or if we increase it just by 1 or 2 to 3%, as you see here, it's just going to exponentially explode. After 14 days, the whole population is going to be infected, right? So as you see here, the infection rate is a very important and influential factor. The other factor is the contact rate. So if I decrease it from 50 to 49, as you see here, the spread of virus is going to go down. That means that the virus is going to stop after some days. So the number of infected people are in decline. But if I increase it from 50 to 51, just 1 more percent, it's going to increase. That means that the spread of virus is growing, right? So that's also important. The contact rate is also important here as well. The initial number of infected people also could be important, but not as important as it was here. So these two factors, the infection rate and the contact rate, these are super important. So that why do we have a flat curve here right now? The infection rate is 2%. The contact rate is 50. Right? So if you multiply 2% by 50, that's 1. Okay, so that's what we have here. If the contact rate multiplied by the infected rate is greater than 1, such as 2.1 multiplied by 50 or 3 multiplied by 50, the growth in your the number of infected is going to be growing. That means it's positive. The spread is positive. Otherwise, if the contact rate multiplied by infection rate is less than 1, for example, 1.9 or 1 or whatever, or if you should decrease 50 from 50 to 49, if these two multiplication, let me read it here. contact rate multiplied by infected rate. So right now, I'm going to multiply this. So right now is right. So the contact rate and infection rate, these two parameters here, is are very important in our model, as I said before. So right now it's 2% and the contact rate is 50. That's why we have a flat curve. Okay, so that means that we have 100 people infected each day. It doesn't grow, it doesn't decay, right? If I change this 2% to less than, increase it or decrease it, the output of our model is going to change drastically. For example, if I decrease it to 1.9, as you see here, the number of newly infected is going to decrease. Okay, or if I so this multiplication of contact rate and infection rate that I showed here, if it's less than 1, your spread is going to go down. Okay, if it's more than 1, it's going to grow. As you see here, you have a growing impact of the virus, so that we have like a kind of pandemic situation here, right? So this 2 multiplication is important. That's what I wanted to show you here. So let me go back to the slides. Hopefully I'm showing you the right slide. All right, so do you see this slide notes on tipping point? Okay.
Yes, thank you.
All right, sure. So if the contact rate multiplied by infection rate is greater than 1, you have exponential growth in your number of spread, number of infected people. On the other hand, if it's less than 1, then you have exponential decay in your spread. If it's equal to 1, which is like a rarely unlikely situation, then the spread of virus is just going to be controlled under whatever number you had at the beginning. All right, so that was our first model, and we did it in a spreadsheet, but that was like a general introduction to the course as well. So this part, we're gonna focus on another model and also introduction to spreadsheet modeling. Modeling a situation. So before you actually start modeling using numbers and equations or a mathematical model, first you need to actually understand the situation, understand the problem, right? So it's important to know the dynamics of the problem, the inputs, what is the output, what goes into the model, what are the parameters or important factors, etc., etc. So having an understanding of the problem is very important step before developing the model. Okay, so that's why most experts actually use what is called as an influence chart, okay, or something like that, similar actually too. And that's actually a way of getting a way out of the technicality of the problem and kind of in a more relaxed way to understand the problem, trying to understand the problem, the dynamics of the problem, the input, the output, what is in the middle of the systematic view. So the influence chart shows a higher level view of the problem or the situation that you are in. It helps you to figure out the in and out of the problem, the relationship between each part of the system. And also it's more conversational than just the technical and numbers and etc. of the model that is more probably difficult or boring. So it's one helpful step before you actually dive into the modeling part. So we're going to use these convention or standards as our books uses, and that's a way of like a standard that helps us to better model or actually develop a chart, which we're going to also use some of these standard in our modeling as well. So what do we have in a problem? We have what is called as output or the objective of the problem or the situation that you're on. We have the input or the fixed data that you have. We have the something in the middle, that's the calculation part that goes to the model. And then you have decision variable, that's also another part of any model. And also random variable that we're going to talk about it in the last chapter when we talk about the simulation, Monte Carlo simulation. So these are all these 5 different parts of the problem or model. The standard or convention that the book uses, it uses the gray rectangle or the gray shade color for the output or the objective. Okay, so it's very good actually if we all follow this same standard, so that it would help us actually when you open up another person's model or the chart, influence chart, it's easier to help you to actually figure out what is the decision variable, which one is actually the output, or what are the inputs of the calculated parts. Okay, so these, it's very helpful to follow this convention and standards. So gray color for the output, the blue color or blue rectangle for the input. Data is very important, right? And that's why we show it with different color. And most of the model, especially if you have a difficult problem, it's going to be a lot of calculation, as you see, a lot of different numbers, like hundreds or thousands of numbers. So because we don't really care about this main part, we don't want to emphasize it, or we just kind of want to hide it from when you, not when you're doing the model, when you want to convey the message or talk to someone or communicate the result, right? So that's why we don't assign any emphasizing color or shape to. That's why we're going to go with blank or white rectangle for the calculated quantities or part. But decision variable, they are very important. That's why we want to actually make a decision. We want to say, okay, this decision, you have to make this and that decision. So that's why we show it with a different color. And we're going to use red or regular rectangle or red oval as they use it in the book. We're going to also use this in the spreadsheet as well. And for the random value, we're going to use green, which we don't have to deal with it for now until the end of semester. We get enough time to go into it. So as you see here, we have gray color, we have blue color, white color, red, and gray, 5. Right. So how does the influence chart work? So you start actually with the end means or the goal in mind. Okay, so you start with actually the end, right? So you start with the output, what you want to do. For example, the number of infected or whatever other models or problem you work with. Okay, so you start at the end and work backward to find all the inputs that goes, all the dynamics, and try to actually figure it out, try to understand. Okay, so we start at the end and work backwards. And then we calculate the inputs, we figure out the decision variables, and we use these standard colors or schematics as the convention goes. So we don't care about the textbook right now because we're using Excel here and also our own means. But in the textbook, if you buy the textbook, it only uses blue and the gray. But it actually recommends to use these 5 colors. Okay, so let's actually apply this influence chart in the previous model or the previous problem, the tipping point model that we use to see how that works. Okay, so we had to start at the end, right? What is the end? The end was to compute the number of newly infected after 10 days or 20 days. Right? So that's the output, right? The number of newly infected, okay? So that's what we go. And that's output, so we're gonna go with the gray rectangle, okay? So now we want to figure out the dynamics of this problem, or the inputs, or the decision variable, right? So we say, what is going to impact the number of newly infected people? Right? What impacts the number of newly infected people? So we figure out that the contact rate is very important, and also the infection rate is important, right? So the number of people that are contacted by the infected people are important, and also the infection rate, which was 2%, if you remember by default, was 2%. That's also important. So these two, now we have these two in mind, we're gonna actually add them as 2 rectangles that comes to this newly infected. Okay, so the number of people contacted, that was one of the that's actually one of the values that can be computed. It's not an input, although the initial value was an input, but it can change from day to day, right? Because, for example, if you remember, for day 1 was 100. If you go with 3%, day 2 was 150, etc., etc. Right? So the number of people contacted, we're gonna, because it's like a medium computed value, we're going to show the white or blank rectangle for it. On the other hand, the infection rate is a constant parameter value. It was 2% by default, but we could change it from what if scenarios or from one problem to other. So that's why we choose the blue rectangle for this. Okay, and both of these factors impact. That's why they add the arrow goes to the number of newly infected. Right. So now we have to figure out. Okay, so first of all, the infection rate, nothing changes that. It's a constant value, right? So we're gonna forget about that for now. Nothing goes into it, but we have to figure out the dynamics of the number of people contacted. Okay, so what's gonna impact that, right? And we work backward from there as well. So, for example, the number with the flu at the beginning, right, which is 100 people, right? So that's one of the factors that's going to impact the number of people contacted, right? Also, the contact rate, which was 100 people, 50 people, that's also an input. So that's why we show it by a blue rectangle. The population size is also important. So that's also one factor. And also because it's a fixed number, it doesn't change. It's an input. We show it by blue rectangle. Right? So you don't have to follow exactly the same, rectangle, whatever, but having a standard would actually help, right? So you could also, for example, go with circles or whatever, but having like the color standard would actually help if you working with other people in a group or whatever. If you all use the same standard and convention, it's going to be easier for you to understand each other work. Right. So as you see here, following these steps, we started from the end, which is the output, and we work backward to understand the dynamics of the model, the factors that goes into the problem. Right. And also the initial number of infected was a constant value that goes to the number of people with the flu today. And if you look further into the model, you see that this is like a cyclical dynamics, because the number of newly infected would actually impact the number of flu today. And this goes on and on each day, right? So this is the dynamic, right? So now that we understand this is, we should have actually started with this instead of going with the Excel, but because the problem was so easy, I started from the model. But for a more complicated problem or model, you better start with this influence chart. Try to actually start with from the end with the output in mind, and then try to work backward and try to figure out what influences each actually factor, what are the factors, and work backward so that you have the whole picture. So you have everything counted in, you have all the inputs, you have all the relationship. And after you have that, then we go to the modeling by Excel. Okay? All right, so that's about the influence chart. Now we're gonna again go back to the Excel. Kind of, I already told you about this. This is very important. You have to your Excel skill is very important. So I talked about the assignment 0 or the Excel diagnostic test, which the answer key is also on either. And also I talked about the Excel tutorial. So I highly recommend you to, no matter how much you're confident about your Excel skill, check out this Excel tutorial and try to spend it's going to take you about 15 or 20 minutes to do the Excel diagnostic test. So it's going to help you understand how much you need to learn. Also, if you're super confident about your Excel, I bet that if you try the Excel tutorial, you're going to find that something that is going to be new to you, and you're still going to learn. All right, so that's about the first chapter. With the first model, an introduction about the decision making, managerial decision making using models, quantitative models, different aspects of the models, and also influence chart. Now we're going to go to the second chapter. Here we're going to see a better and more elaborate understanding of the spreadsheet modeling. And you're going to learn about different functions that are in Excel that you can use. For example, I used actually the minimum. If you remember, we can also have, there are other bunch of other actually functions that we can use. For example, if, maximum, etc., etc. We're gonna also learn about the logical. You're gonna learn how to actually try to develop a model that is logically correct, and also it's clearly laid out so that if you build a model today and you come back to it a year from now, it would be really helpful to you, or if you want to communicate with other people or share your model with a group of other people, it would be helpful to actually clearly lay out your model. So using headings, using different colors, using, like, for example, boldness, clearly stating everything, the variables, the parameters input, using the colors that I mentioned on the convention, it's going to be helpful for your own sake and also for the group work. Readability. So we're going to talk about range names if we get the chance today. You can also comment on a cell if it's too complicated and you need to actually communicate more about a specific cell or specific thing. You can actually put a comment in Excel. And there are a great way for what if analysis in Excel that we're going to use today if you get the time. So to learn about this, just an example, we're going to do another model, another problem, which is a simple profit model. So I mentioned actually the break-even point, if you remember. So here in this model also, we're going to talk about the total cost and total profit and total revenue, etc., etc. So this is the problem. Suppose a company makes a product that it currently sells for $30. So that's the price value that you can sell the product, okay? $30 each. And also suppose that the company set up to make the product, they have to invest $10,000 as a fixed cost. And for each product that they produce, they have a variable cost of $14 per piece, okay? And the demand, suppose that is currently 1,000 fixed items per week, okay? And we also assume, for simplicity, that whatever they produce, they actually can sell. That means that we know the demand. We, of course, we don't, in reality, we don't really know the demand. We can actually predict it, make a prediction, but all prediction have errors, right? So for simplification of this model, we're going to assume that we know the demand $1,000 items per week, and it's fixed. And we assume that whatever we produce, which is 1,000, we're going to sell it, right? So we want to see what is the profit if we produce 1,000 items per week and we sell it, okay? And later on, if we have time, we're going to make the model actually more advanced and more complicated. So we're going to assume that, okay, what if we relax this assumption that whatever you produce, you can sell, okay? What if actually you produce more than you can sell, right? So suppose we can actually talk about the salvage value. Suppose that if the salvage value for an item that is not sold is $10, okay? So we want to see how would that impact the problem or the model, okay? So let's just start with the influence chart that we just learned, okay? So we want to understand, this is a very simple problem. You really don't have to do this, but I want to just show you the scientific approach for this, which is the influence chart. So we start with the end or the goal in mind. The goal, what is the goal? The total profit, okay? So what goes into the profit, right? So for the profit, that's actually your revenue, your total revenue, subtracted by total cost, okay? So two factors, revenue and cost, okay? So what goes to total revenue and what goes to total cost? What goes to total revenue is, of course, the price tag, how much you can actually sell the items, and also the demand. That means how many you can actually sell, which also here is how many you produce. Okay? That's a simplification assumption that we have made. And also for total cost, we have the unit cost, we have the fixed cost, and also the demand. That's how much you actually produce. Okay. So these four factors are going to impact these two other factors, okay, like this. So unit price and demand is going to impact the total revenue. The demand, the unit cost, and the fixed cost is going to impact the total. Right? So it looks like we have figured out all the relationship here, right? So now we are ready to go to a spreadsheet and model this. But this, as I said, this is a very simple problem. That's why we didn't really need to do the influence chart. But for more complicated problem, before you head into the dive into the modeling using a spreadsheet or mathematical modeling, you need to find the dynamics of the problem. So you use the influence chart, starting at the end, finding the factors and moving backward until you have everything, the big picture from the problem. Okay, so unit price could be a decision variable, demand could be a random variable, but that's not what I want to talk about now. Okay. All right, so let's go to spreadsheet. So first here, I'm gonna call the model. I'm gonna name the model here with the problem. And also it's easy, it's actually very helpful when you save the file, you give it a name that you can actually remind you what the problem was. So for example, here we say the simple profit model or the profit model. Simple profit model. So I'm gonna write the name of the problem or the model here. I'm gonna make it bold. And then now that we had the influence chart, we figured out the inputs, the dynamics. I'm gonna put the inputs here and then I'm gonna list them, okay? Inputs, both here and here, I'm gonna list them. So one of the inputs was the selling price. Selling price, which was $30. The other one was unit cost. We had unit cost, we had fixed cost. Unit cost was $14. And we had fixed cost, that was $10,000. We also had demand, which was 1,000 items. Right. So I talked about using a convention for naming or actually color, a specifying color. So for the inputs, if you remember, I said using the blue one, right? There is actually another Excel file. It's called my styles. That's also in the IDLER. Okay, so if you open up my styles, let me share this with you. It's very actually simple. My styles. Okay. So this is the my styles. It just shows the color that I showed you with this line here. So the output is gray, input is blue, calculated quantity is blank or white, decision variables are red, and random variables are green. If you open this and let it open, and then come to the home button here, and in the styles, go to the, okay, do you see this? No, you don't. You don't. Work three. All right. So if you go to the home button here, home page, and go to the styles group, right? The cell styles, you can go to the measure styles. So right now you have normal, bad, whatever. These are, in Excel headings, etc., etc. So, but I want to use my own styles that I showed you, the color, the gray for output, for input, etc. If you click on the merge styles, if the my styles file is open, you can actually see it here. Click on it and then click OK. So what happens now, if you go to the sales styles and open it up, you actually can see the styles that I have in my styles file, which is for calculation, it is blank. For decision variable is red, for input is blue, for output is gray, for random variable is actually blue. Okay, so now you have actually this. So now the inputs we said are blue, so I can highlight this and use my own style as blue. Okay, or if I have random variable, I can use my style red or output whatever. Right. So okay, so that was for the inputs. All right. So another part of the problem or model is the calculated quantities. What quantities we need to compute here? We need to compute the total revenue. We need to compute the total cost, and also our output, which is the total profit, okay, or profit. Okay, so here I'm gonna put the calculated quantities. Calculated quantities. Okay. I'm gonna make this bold, and below this I'm gonna write the total revenue and total cost. And here, what is the total revenue? So the total revenue is equal to the selling price. I'm going to click on this, a star, which is multiplication, multiplied by how many you can actually sell, which we assume that we can sell as we know the demand, and we're going to produce 1,000. So that's the total revenue. And I can say that this is a dollar value, so it's going to go to $30,000. And total cost, for total cost is equal to the fixed cost plus the unit cost. So fixed cost plus unit cost 14 multiplied by how many we produce, which is the demand, 1,000. So that's also 24,000. Right? All right, so I'm gonna, these are the calculated quantities. So calculated quantities, as you see here, are left blank. So I'm not gonna give this color. The other part of the model or the problem is the output. Okay, output. I'm gonna make this bold, and below that, the output is profit. Profit, and the profit is just subtraction of total cost from the revenue, which is the other way around. So that's total revenue minus total cost. Okay. And the output, we said we're gonna show it by gray. Okay. All right. So now we have that. Any question? So our total profit, this is like a very simple computation. Our profit, if we make $1,000, 1,000 item per week, and the selling price is $30, the unit cost is $14, and the fixed cost is $10,000, and we're gonna make $6,000 in profit per week. So let's see the rest of the problem. Okay. Screen 2. So simple profit model and Excel section, we went over this, what goes in each input. So we had fixed cost, unit cost, price, demand, etc. Decision variable, what was our decision variable? The decision variable actually is how many to produce, which we actually relax it here. We assume that we produce as many as demand, right? So it was a fixed value. Then we had calculated quantities, and the output was the goal was the profit, which we computed. The next thing is we want to actually build a one-way data table, and also we want to do graph. So what is a one-way table? So we want to say, for example, for different values of the decision variable, which is we assume that is equal to the demand. For example, we want to have the output for based on different values of demand. So for example, right now we had it for 1,000. We want to see, for example, what if actually the demand was 0? What if actually the demand was 1,000 or 2,000 or 3,000, etc., etc. So we want to do this computation and calculation and what if scenarios in Excel, and also we're gonna plot that. Okay, so let's see what is the best. So we want to create a one-way, what is called as one-way table, one-way data table. So here I have demand and then other quantities in our model. So for example, total revenue, total cost, and profit. Okay. So I'm gonna leave the first row under the demand. This is the table that I want to create. The first value under the first cell on the demand, I'm gonna leave it blank. And then here I'm gonna go with the other values that I want. For example, I want 0, I want 1,000, which is there. I want 2,000, 3,000, etc., etc. Whatever values. And then for others, because these are calculated or functions, I'm gonna reference them here. So for example, total revenue is equal to this cell. Total cost is equal to this cell. Total cost is equal to this cell. And profit is equal to this cell. Okay. So now I grab all of this, including the first row, and then I go to data, and then I go to data. I go to the forecast group. There is a what if analysis here. I'm going to go to what if and click on the what if analysis, and there's a data table. So I click on the data table. So it opens up this window here. It says row input cell, column input cell. Because my values are in column, this function or these calculated values, I'm going to put them in column, right? So I'm going to skip over the row input cell, and I'm going to go on the column input cell. What is the value that I want to change? This value be changed based on the demand, different demand values, okay? Based on different demand values. So I'm gonna go to this 1,000 here. Okay. So automatically what happens is for different values of this demand that I have listed here, it actually calculated these values that I wanted: the total revenue, the total cost, the total profit. If I make the type of the value here, which is dollar values. Right.
Hello,
So,
Professor.
Yes.
What was the value for the column input cell? that you just did?
For color input?
Column, input cell, column? I missed
Oh.
that.
Oh yeah, so what I did was I actually selected this table, these cells here, and then I went to data and to the what if analysis data table, and I skipped over row cell. And for the column cell, I said that the value that I want to change based on is the demand. So I selected this demand value here.
Okay, got it.
So what actually this gives Excel is it says, okay, this is the relationship. The relationship is total revenue. These are all, if you remember, these are all linked or referenced here, right? So it knows the dynamic of the model. And then I said, okay, demand is these different values, okay? And then when I specify that, when I specify here in the what if analysis that I want the column values to change based on this demand. So it's gonna actually input this 1,000 to 2,000 and 3,000 instead of this 1,000 here, and then it's gonna compute these total revenues, total costs and profit, and it's gonna print it out here. Okay, so very efficient, very fast. And imagine if you had it like, you know, for 4,000, 10,000, 2,000, like hundreds of numbers with just one click, it would generate thousands of numbers for us without having to compute it individually. Okay. All right. So now this is again our numbers, and it's not the best way to communicate or renders the output to you know, your manager or to other people in your group. So that's why we want to use a graph. Okay, so let's actually do a graph. So I'm gonna actually plot all of these values: the total revenue, the total cost, and profit. Okay, so let's do that. So first, I'm gonna go with the total revenue. For demand equal to 0, then I'm gonna go to insert, to the chart part, the scatter chart here. So I'm gonna go with the axis title. These are demand. And this is, I'm gonna say dollar amount, because I'm gonna show different values here, different actually different outputs. For example, total revenue, total cost, and profit. I want to show them. I want to plot them in the y-axis. So y-axis represent actually the dollar value, dollar amount. So instead of saying total revenue, total cost, profit, all of them are in currency dollar amount. So I'm going to say dollar amount. Okay, and you can name your graph. It's always best to actually name your graph for problem. So I'm going to say, you know, a scatter chart, whatever. XY scatter chart. Or whatever other names that you find suitable for. Okay. So this is only one actually factor, total revenue. I also want to have the total cost and profit. So to do that, if you have a PC or Windows, if you right click on this graph, it's going to open up this menu here. So you can actually use select data. If you select data, it's going to bring up this window. So this window, it has series here, which is the chart name here, and the values here. It has 3 buttons here: remove, edit, and add. So I'm gonna first edit, because the name of this series is series. I want to change it actually to whatever it is, which is the total revenue. So I want to change the name of this to total revenue. So I'm gonna say total revenue. So if I click on this, now it says total revenue. Now I want to add the other columns as well. So I'm going to add the total cost. So I'll click add. It's going to build up this. So I'm going to name it total cost, total cost. And the X series values are gonna stay the same, so they're gonna be these values. And for Y series, make sure that you click all of it and then hit OK, and then select these values from 10,000 up to, from H6 up to H9. Okay. Hit OK. Add another one, which is the profit. I'm going to call it profit. The series X value or X values are the demand here, which is 4 values from 0 to 3,000. And for Y values, I'm gonna select from I6, okay, from the second row or third row up to the I9, and hit OK. All right, so now I have this, but it's really difficult. It doesn't show, you know, what is the blue one, what is the orange one, what is the gray one. Okay, so it's very good actually to have a label for these. So I'm gonna click on this plus sign and go on the legend. Okay, so go on the legend, click on this little triangle here. It says, do you want it on the right? Do you want it on the top? Do you want it on the left? Bottom. I'm gonna go on top. Okay, if I go on left or right, it's gonna make my graph smaller. So I'm gonna go on the top, for example. If you go click on the top, as you see here, it just shows you the legend of this. So you know that the blue one is total revenue, the total cost is the orange one, and the profit is the gray. Okay. Any question? So this shows the dynamics for different actually values of demand, so that for whatever you sell, which is, you know, we assume that is equal to demand. That means that we assume that whatever we produce, we can actually sell it. Okay, so for values from 0 to 3,000, if you can see the relationship, so the profit or the break-even point is around 600-ish. That means that your total cost is equal to total revenue. So you don't make profit, you don't make money, you don't lose money. But more than that, you're gonna make a profit, and the profit is start from 0 up to about 40,000. And if you make less than 500-ish, you're gonna lose money. That means that your cost is more than your revenue. So we did this simple profit model. We figured out what goes into the model, the input to output decision variables. We built actually a plot. We plotted the lines, the total revenue, total cost, and total profit. So let's go to the next one. We also did the one data table. How does the demand affect the revenue and cost and profit? We did that as well. So this actually shows you how we can actually this slide number 14 in the introduction to a spreadsheet model. It shows you how to do the one-way data table. Okay, so with detail, just go to the data tab, data tools, what if analysis, data table, skip over the row, go to the column and click demand. Okay. So what next? We want to actually make an extension on the model now. So we assumed whatever we can make, we can sell, which is a simplifying assumption, which is not true at all. Okay, in reality, you could actually produce more than you can sell, or you could produce less than you can sell. Okay, so now we want to actually add this complication into the model. Okay, so we want to go with the salvage value. Okay, and also we want to do a more Excel thing here. So we're gonna do range names, which is going to improve readability. Okay, so let's do range names. What does range names mean? What does range name mean? So let me open up again the Excel file that we have. So if you have this Excel file, and you right now, because you have built it, you know what it is. You know what the relationship dynamic, etc., etc. The only thing that we have done is to make it more readable is this little blue color and gray color here, which shows you, okay, this is This is output, these are input variables, and these are, immediate computation. This is in the middle computation. Right? But if you give this to someone else who want to try to see, what are the dynamics here, what these cells stands for, how these values are computed. So if someone open up this and click here, it says B5 multiplied by B8, right? See here. Also for this one, it says B7 multiplied by plus B6 multiplied by B8, okay? Or for example, for profit, it says B12 minus B13. So these are not really readable. Of course, you can figure it out by just looking at what is B5. So B5 is actually selling price, or what is B8, which is demand. But you actually, what if actually you could actually name this? Instead of B5, you could say selling price. Okay, so this is what we want to do. We want to do that. So if you go to the formula tab here, you're going to see on the define numbers, you're going to see what is called as create from selection. This is actually for range names. So this is what I'm going to do. I'm going to select the selling price and the numbers in front of it, which is 30. I'm going to go to the formula tab, the defined names group, create from selection. So it gives you this window. It has top row, left column, bottom row, right column. So it means what would you want the name to be? I want the name of these two selection to be the column on the left. Okay. So for example, we have 30 here. The left column says selling price. So I want selling price to be the name of 30. Okay. So if I click OK now, it says instead of, see, right now here it shows B6, here it shows B8, but because I changed this cell, right now instead of B5, it's actually selling price here. Okay. I can also change this name. Instead of B6, I can name it unit cost. Okay, so I'm going to select all of this again. Go to the formulas tab, create from selection, left column, hit OK. So right now, all of these actually changed their names. So for example, this used to be B8, right now is demand. This used to be B7, right now is fixed cost. This used to be B6, right now is unit cost. I can also change this. Right now it's B12. This is B13. So I want this to be total revenue, and I want this to be, instead of B13, to be total cost, and I want this to be, instead of B17, to be profit. So this is what I'm going to do. I'm going to select these two. I'm going to go to the formula tab, create formula from a selection. All right. I think I have too many softwares open, so my computer is a little slow. So I'm going to hit OK here, and the names have been implemented. So right now, this is no more B12, it's total revenue. The name of this cell is not B13, it's total cost. I can also change the name of this cell. So right now it's B17, I want to change it to profit. So I'm going to select this profit, the column before that, and I'm going to go to formulas, create from a selection, and hit OK. And this is profit, right? Okay. So this is much better now. And also for the computation part, if you see the formula, it says B5 multiplied by B8. I can actually change this. So I can actually change this to update this. So it would total revenue. What would be total revenue? Total revenue is the selling price multiplied by the demand. Okay. So if you click it, it says selling price multiplied by demand. It doesn't say B5, B6, B6, whatever. And also I can do this for this right now. So right now, the total cost, it says B7 plus B6, which doesn't make sense. You know, you don't understand what it is. So I can go with this. The total cost is the fixed cost plus the unit cost multiplied by the demand. Right? Very informative and easy actually to understand, right? So it improved our readability of the model. And also here for the output, it says B12 minus B13, which we don't know what it is. So I'm gonna make it more readable. So I'm gonna say the total revenue minus the total cost. Right? See, total revenue minus total. So if you had done this before, if you name your inputs, and then before that, after that you do this formula, then it's actually easier and more. All right. So we learn about range names to improve model readability. Here in this is a slide number 15. It shows you exactly what you need to do, all the details to do the name changes, the name range. Next, this is what we want to. So now we want to actually make our model a little bit more complicated. So we're going to add this salvage value, or the assumption, or relaxed assumption that it's not that whatever you can produce, you can sell. It's possible that you could produce more than you can sell. So you would have, the concept of salvage value from leftovers, and also decision variables, the number sold, the number left over, the total revenue, total cost. So this is what we want to do. So we want to add the concept of leftovers or overproduction, which is going to be salvage value. Okay, so we need to add more inputs on decision variable, etc. So right now we have 4 values as inputs, but we also want to implement the salvage value. What was the value of salvage value? $10. This is $10, right? Right. So here I'm going to add actually another inputs here. I'm going to call it salvage value. And that's $10. $10. Here I'm going to go to a style, and I'm going to make. I could also do the name change here. Right. And I want to add a decision variable, which is the production. We assume that we produce as much as the demand, but that's not realistic. So between the inputs and calculated here, I want to add the decision variable. So we need to add more rows here. So if you click here, you can, if you right click on here, it says insert. So it's going to insert one more cell. I'm going to repeat that one more time. Right. Don't have to do this. All right. So here there's going to be our decision variable. Decision variable. So I want for readability, I'm gonna put it on the left side, and I'm gonna make it bold. I'm gonna have to add another row here. So here I'm gonna add production as our decision value. So production shouldn't be bold. It's a decision variable. I'm going to make it on the right side. And here is the value. It has to be the value. Right now, we don't know what it is. And because it's a decision variable, I'm going to make it the style of decision variable. Okay. So suppose that it's 1,000, as much as the demand, but we can actually change it because it's a decision variable. The other calculated quantities, the number sold, the number left over, and we have to also update the total profit and total cost because of the leftover and the salvage value. So we have to modify actually these values. Okay. So forget about our computation from before. I'm gonna put this graph away because we're gonna have another. Actually, this is another problem. Okay, so calculated quantities. We need to have number of leftovers, number sold, insert, number of leftovers, and that's it. Okay, so number sold and number of leftovers. And these are also calculated quantities. So numbers sold could be what? How do you compute the number sold? What do you think from all of these values that we have? What is the relationship here? What should it be, the number sold? Not the value of, I mean the relationship. So the number sold, it should be, should it be equal to demand? But the number sold, because we have leftovers, it could be at maximum, it could be the demand, right? But it could be also less than the demand. If you produce less than the demand, the number sold, it would be less than the demand. Right? So that would be the minimum of demand and production. For the maximum. I'm gonna name change this to so that's the number sold. This shouldn't be the currency, it should be general value number. How about number of leftovers? So the number of leftovers, it would be that much you produce minus whatever you can sell, which is the demand. And if you produce more, so it would be the production minus sold.
Professor, a quick question. Should production and demand, should those just be general numbers or should they be dollars?
No, the production, that means the number of items that you produce. So it should be general numbers. So we're talking about the decision variable, how many to produce, right? How many items to produce. So we're talking about like numbers, not currency.
Okay, just because on your doc it has a dollar sign next to it. That's why I was confused.
I think I changed it.
On the production value? E13?
Oh, sorry. Yeah. Okay. Yeah. Thank you for letting me know. I have to make this general. Yes. Now it's clear. Yeah. Thank you. All right. So number sold, number of leftovers. So how should we compute the number of leftovers? Number of leftovers is if the demand is less than whatever you produce, so the amount of produced minus the demand. If that's a positive number, then that's that. If it's not if it's a negative number, that means that you have produced less than the demand. Then we don't have leftovers, right? So it's a minimum of no, it's the maximum. Yes, it's the maximum of these two. So it's the maximum of the amount that you produce minus the demand. The demand also shouldn't be dollar value and 0. So let me change the demand value to numbers instead of currency. Okay. Right. All right. So let me check this if it's correct. So if we produce 1100 and the demand is 1000, that means that we have 100 leftovers. So this is correct. And how many we sold? 1000. If we produce 900 and the demand is 1000, then we sold 900 and the leftovers is. So this is correct, right? So how about the profit? What should be the profit with this additional thing that we did here? So the profit before that is just total revenue minus total cost, which is true. But so that means that we have to change actually the total revenue and total cost. The total cost, the total revenue here is selling price minus multiplied by demand. Is that correct? It's not correct because it's how much you can actually sell, right? Number sold. So instead of demand, I have to say number sold. So let me actually make this also, name this. So total revenue, it should be number sold, right? So total revenue is the selling price multiplied by number you can sell, right? How about total cost? So the total cost right now is fixed cost plus unit cost multiplied by demand, but it's actually instead of demand, what should it be instead of demand? What is the total cost? Fixed cost plus how many you produce multiplied by unit cost, right? How many you produce is actually the production, right? So instead of demand, I should go with the production. Okay? So right now, everything is right? Okay. So now we can actually do this analysis. If I produce, if the demand is 1000, you know, if I produce 900, I'm gonna have 4400 profit. But if I produce less than that, 800, I is still gonna have profit. If I produce say 500, I want to see, as you see here, our profit is gonna go down. If I produce 500, we're gonna have negative profit. That means that our total cost is greater than total revenue. Right? It's still negative. 650. So that means that your break-even point is between 600 and 650. And if the production is greater than the demand, say 1100, you're still going to make profit, but your profit is going to go down because the salary, because if you have leftovers, you can actually, the salvage value is $10 instead of $30 that you could sell it. Okay, so it costs $14 to make, and the salvage value is $10. So if you produce more than the demand, you're actually kind of losing money in the total cost, in the cost of production, because the unit cost of production is 14 and the salvage is 10. So it's like $4 cost or more cost than revenue, right? Any question? So I wanted to do another two-way data table, but we don't have time for that, and I don't want to too much information for the session, which we already kind of did. All right. Any question? All right, that was a lot of information. I think it depends on how much you knew about Excel, I think, but I think we learned a lot. If you didn't have much information about or a skill about Excel, we learn how to do analysis, to change the names, to do the one-way table, do a lot of computation automatically, and also we learn about the standards and conventional way of approaching a model. The quality of a good model is that you don't have to touch a lot of things in the computation part, make sure that all of your computation is linked to the inputs and the values that you have, so you don't have to change the numbers in between. Just by changing the input values, your output is going to automatically change. And if that's so, then you have a good built model, like Excel.